All right, so now we want to tackle this this question of how do we choose, say, 4 books from the 7 that are available to us if we don't care about the order in which the books are selected. All right, so this is like if you know you're going to a cabin or something that doesn't have Wi-Fi and you need to bring either 4 physical hard copies of books that you want to read, or you want to pick 4 books to download to your Kindle or your iPad or whatever device you happen to be bringing. And the order in which you put them on there doesn't really matter. Later on you'll select an order to read them in, but that's not what we're asking right now. Just how many different ways are there of choosing 4 books from the 7 that are available to you if you don't care what order they're selected in? All right. So let us think about how to go through this, not from a fundamental counting principle point of view first, right? Let's think about it in a more basic way than that, right? Let's just try to tackle this question directly. So basically what we're trying to do here is to figure out all of the collections of 4 books from the 7 that are available to us, where in any given collection of 4 books, the order in which we write them doesn't matter. All right, so as long as, say, books 1, 2, 3, and 4 are in the collection, they're in your backpack, it doesn't matter if you put in book 4 first or book 3 first, it's still the same collection of 4 books. So this is very similar to the unordered coalitions from the weighted voting theory section that you just took an exam on. And so, let's just start listing some out. We're not going to list all of them, but let's list some of them. So, you could have book 1, book 2, book 3, book 4. Right, that's one of the collections of books that you might have. You could have book 1, book 2, book 3, book 5. Or you could have book 1, book 2, book 3, book 6. Or you could have book 1, book 2, book 3, book 7. And then those are all the ones that you could have with books 1, 2, and 3 included. So now, maybe you keep book 1 and book 2, and you change book 3, for instance. All right, so next, being systematic about this, book 1 and book 2 stay the same. But now let's change book 3 to book 4. And now notice that if I were to put, say, book 3 here, well then what I've got here is books 1, 2, 4, and 3, but the order doesn't matter. So that's actually the same as what I have here, books 1, 2, 3, and 4. So that actually won't work, right? I can't put book 3 there because I've already got that collection of books right there, first on my list. So that's not going to work. All right, so let's get rid of book 3. This means that the next book I would have to put down, if I'm trying to go in some sort of logical order here, would be book 5. Right, I don't have books 1, 2, 4, and 5 anywhere else in my list yet. So that would be a brand new collection. And then do the same thing, right? Book 1, book 2, book 4, book 6. Right, that's a new collection of 4 books, and so on and so forth. All right, so you'd keep doing this ad nauseum, and eventually you would come up with an exhaustive list of all the possible collections of 4 books from 7 that you could pick. Now, this is going to be tedious, I think is probably the most polite word I can use for it. So let's try to figure out a better way to do this. All right, there's got to be a better way. So let's think about a better way that we can do this. How many ways would there be if order did matter? Right? So if order did matter, all right, so here we've already answered this question, but I'll go through it again. You have to pick a book that goes first, pick a book that goes second, pick a book that goes third, pick a book that goes fourth. Now, the reason why I'm asking this question, right, why am I bothering to ask what happens if order does matter? Well, I want to ask this question because we know how to answer it. All right, so it's a very closely related question to the one that we actually care about, which is when order does not matter. And we already know how to answer what happens if order does matter. That's why I'm asking this question. All right, so first let's address this. Can we answer the question if order does matter? And we've already done it, so we know the answer is yes. Then what we're going to do is try to come up with a strategy. Is there a way that we can use this answer, when order does matter, to somehow address that order is not supposed to matter for us? Okay, so this is our game plan. And now we've already seen that we know how to answer this question. When order does matter, we have to pick a book that goes first. We have 7 total options for how to do that. Now we've chosen a book to go first, so we have to choose a different book to go second. 6 options for how we can do that. We've chosen 2 books from the 7 to go first and second, so we have 5 left to go third, and 4 left to go fourth. Generalized fundamental counting principle. So this is the generalized fundamental counting principle. It tells me that there are 7 times 6 times 4. I don't know why I would write it that way. That was a silly typo, but times 4 times 5 is the same as times 5 times 4. So there's that many different orderings of the 4 books chosen from the 7 that we have available. Now, what we want to do is think about what this is really saying. All right, what this is really saying is that, if I go back here for a second, let's look at this collection of 4 books from the 7. Right, there's book 1, 2, 3, and 4 in our bag. And what this calculation we just did down here is saying is that if order did matter, well, there would be a lot of different copies, right? A lot of different carbon copies of those same 4 books that are being counted multiple times. And this is because we just calculated this thing when order does matter, but for us, it's not supposed to matter. So let me make this explicit. All right, what we've said here is that if order does matter, then I'm going to use the angled brackets, just like we did for sequential coalitions, to illustrate that order matters here. All right, so if order did matter, then what we've said is that book 1, book 2, book 3, book 4 is one ordering of 4 books from the 7. And this would be a distinctly different ordering. It's counted as a different collection than book 2, book 1, book 3, book 4. Even though for us, right, in the actual question that we're trying to answer, these collections would be the same, right? They'd be the same 4 books that are in our backpack. And, there would be a lot of these things, right? We could have B2, B3, B1, B4, right? This is another way of reordering the same 4 books. And all of these are being counted as distinct collections of books in this number up here. Right, so that number up there has sort of encoded in it every one of these different orderings of the same 4 books. All right, but in our actual way of solving this problem, right, our actual way of counting these things, those different orderings of the same 4 books are supposed to boil down to one collection of 4 books, right? It's just books 1, 2, 3, and 4 that are in our backpack. We don't care what the order is, just that it's those 4 books. So, this number here in the red box, 7 times 6 times 5 times 4, this number is going to be way too big right? And it's going to be way too big because of what we just saw down here, right? The same 4 books can be reordered in a lot of different ways. And that just means that the same 4 books are going to be counted multiple times in this number that's in the red box here, right? So that number is going to be way too big. So here's my strategy. This number in the red box is way too big. And we know why it's too big. It's because the same 4 books are being reordered and counted a bunch of different times, even though it's the same 4 books. So here's my question for how we can address this. Say we've chosen our 4 books. How many different ways can those 4 books be reordered? That's really the question that we have to address. Right? So how many ways can 4 books be reordered? Right? If we can answer this question, then this will tell us how many different times, right? How many carbon copies of books 1, 2, 3, and 4 are present in this calculation in the red box right there. In other words, it's going to tell us how many times too large that number in the red box is than the actual number that we want to calculate. Right? It's going to tell us how many times, how much redundancy is built into that calculation. That's what this number of reorderings is going to tell us. Right? It's going to tell us how much redundancy is built into that calculation we just did. And now, this is another fundamental counting principle question. And it's one that we've actually answered a bunch of times by now in this class. Most notably in the context of sequential voting. Right, so the question that we have to answer here is, how many different ways? Right, so how many different ways can these 4 books be ordered in a sequential coalition? We've got 4 options for a book that can go first, 3 options for a book that can go second, 2 options for a book that can go third, and then 1 option for a book that can go last. The generalized fundamental counting principle says to multiply all these things together. And this is for factorial reorderings of the 4 books. 4 factorial, we know what that is. That's 24. Not too hard to calculate that. Okay, so what we've said here is that there are 24 distinct reorderings of any group of 4 books that we pick. Right, so if I had gone through this whole song and dance up here, right, this right here, if I had taken this to completion all the way out to every single possible reordering of books 1 through 4, there would have been 24 total reorderings if I had written them all out. So what that tells me is that the collection book 1, book 2, book 3, book 4 is accounted for 24 different times in that number. All right, so this is not just going to be true for books 1 through 4. This is going to be true for any collection of 4 books that I pick. Every single collection of 4 books that I pick is going to be counted 24 times in this calculation that we made here when the order mattered. So, this tells us exactly how to address the fact that order is not supposed to matter for us. Right? If we know that every one of the collections of 4 books that we choose is being counted 24 times in this calculation up here, right, in this thing in the red and now blue box, well, that tells us that that number is 24 times too large. Right? It's 24 times bigger than the number is supposed to be that will actually answer our question. All right, so the idea here is that the total number of of ways to choose 4 books from 7 where the order in which you choose them doesn't matter. Right? The order doesn't matter. Well, this is going to be the number of ways if order did matter. And what we're going to do is go ahead and take that number and we're going to divide it by basically the redundancy that's built into order mattering. Right, so we're going to divide out the number of ways of reordering any collection of 4. Okay, so this is the idea. All right, we're going to first address the problem that we know how to handle, which is how many ways are there of doing it if the order did matter. We did that on the last page. This is 7 times 6 times 5 times 4. And we're going to divide that by the number of ways of reordering any particular collection of 4 books. And that's 4 factorial. 4 times 3 times 2 times 1. And now, this number looks like a kind of a mess, right? This doesn't look like a great answer. And one really beautiful thing about the way that these problems always work out when you're doing a problem like this is that these numbers always cleanly divide one another. You will always get an integer answer for this, which makes sense, right? There shouldn't be 7.5 ways of reordering the books. It should be 7 or 8, right? It should always be an integer. And that turns out to be the case here. So let's just cancel out things that can be canceled out, right? We can take a 4. Since we're multiplying through everything on the top and the bottom, cancellation's relatively straightforward. The 4's cancel. 3 and 2 together, notice is 6. And so the 6 can cancel with the 6, or with the 3 times 2. And so what we're left with, after canceling, is 7 times 5, which is 35. So, this tells us there are 35 ways of choosing 4 books from the 7 available where order doesn't matter. All right, and again, the strategy is figure out all the ways that they could be chosen if order did matter. That's our numerator. And then divide out the redundancy that's in that number. In other words, divide out all the ways that those 4 books you just chose could have been reordered themselves, which will tell you how many times too many that every collection of 4 was counted in this number in the numerator that's too big. All right, so this is the idea. And there's a lot more to say about this, which you'll see in the next video.